Alright, welcome back to EC 3030. Before today's lecture, I want to have a few announcements. The first one is the homework 1 has been posted last week, and I suppose you may have already started. So the due date is this Friday, and 11:59 p.m., so basically before the midnight. So you are supposed to upload a PDF to the Canvas. If you have any questions regarding the homework, feel free to join one of the sessions of the office hour. And if you look at the syllabus here, so my office hour is tomorrow, Wednesday, 11 to 12, and also TA Victor office hour, like the, let's say, Thursday, 10:30 to 12:30, Friday, 4 to 6. So feel free to join those office hours in case you have questions regarding the homework. So after today's lecture, you should be able to finish all the questions. Any questions? Okay, so let's get started on the lecture. A quick review of last lecture. So we have started the discussions on this lecture 5, physics of the semiconductor, on the carrier statistics. So let's have a quick review of what we have discussed so far. So here, this is the energy band diagram for the electron in the semiconductor. And we have those two definitions. This valence band is on the bottom, and then the conduction band is on the top. And between those two, we have this band gap where the electrons cannot occupy those energy levels. And here we have two edges. The edge between the conduction band and the band gap is called EC, and the edge between the band gap and the valence band is called EV. And for the silicon, the band gap is about 1.1 electron volts. So as you know, at absolute zero temperature, then all the electrons are filled in the valence band, and the conduction band is completely empty. But with finite temperature, when you increase the temperature, so electrons may have some kinetic energy to jump over this barrier, and then the electrons can be in the conduction band, and also you create hole in the valence band. So that means there are some probability for electrons to occupy on those empty states in the conduction band. And later we're going to use this Fermi function to describe this kind of probability for electrons to occupy on the empty states. So that's why we introduce this Fermi level, EF, and also the Fermi function in the next slide. So this is why we are interested in this Fermi function, because it tells you the electron probability to occupy at a particular energy level. Of course, we are interested in the levels in the conduction band. And then the Fermi function is given by this formula, Fe. E is the energy level of the electron. F is the probability. And then it's given by this 1 over 1 plus exponential E minus EF over KT. EF is the Fermi level. It's a reference level. So here we have some conclusions saying that at T equals to 0 Kelvin, then this Fermi function is a step function. And below the Fermi level, then the probability to find the electron is always 1. And above that is always 0. That means all the electrons in the valence band. And here on the top, in the conduction band, it's completely empty. But as you increase the temperature, then this Fermi function will spread out. And then we have some finite probability to find the electrons here in the conduction band. So the Fermi level is a reference level because at this level, the probability is always half. Of course, this is a conceptual level. It's not real. It's just for reference. And then we have some discussions on the Boltzmann approximation on this Fermi function. So the idea is to look at those two tails, because this tail will enter the conduction band, and we want to simplify this tail's function. So we do this so-called Boltzmann approximation, where the energy for the electron is much higher than the EF. So let's say much larger than kT, the thermal energy, or let's say is much larger than 3 kT. That will guarantee this is much larger. So then, if you do this approximation, this Fermi function will be simplified to this exponential decay function. So you have this exponential tail here, and then the probability will gradually become 0 as you increase the energy up. And similarly, you can do the approximation on the lower end, and then this probability will gradually approach 1 for the valence band. So this is what we have discussed in the last lecture. Any questions? If you have a question, feel free to type in, or you can unmute and ask. I got one question. What is exactly meant by energy level? So energy level means the electron's energy. So energy level means, let's say the electron's energy is higher or lower. So we can describe that into a level. So level is just a value. So let's say electron's energy higher or lower. So it's just a level, because there are so many levels in the semiconductor system, because we have this band, and then the electron can occupy at different levels with different energy values. Or in other words, if you recall the very simple atom, as we discussed earlier, right? If you have individual atoms, then you have the orbit surrounding the nucleus, and each orbit is a discrete energy level. But in the semiconductor solid, since we have so many atoms, then we have so many levels. So then those levels can be continuous. So electrons can have continuous states of the energy with analog value on the energy values. Okay, so then let's discuss something new today. So then we need to consider how the electron actually occupy on those levels. And we need to consider two factors here. The first one is the available states, and second one is the Fermi function. So let's assume a simple example like this. So for example, here we draw a ladder, and let's say each level, so here has, let's say, 10 available states. That means you can at most put 10 electrons here. And the ladder, let's say, the higher the level, then that means the higher the energy of the electron. And here we assume that there are many levels like this, and each level can occupy at most 10 electrons. Of course, this is a toy model. It's not a real case, but let's use this as an example. So this is available states, and then we need to consider how the electron actually occupy on those states. Then what you need is the Fermi function, because that tells you the probability for the electrons to occupy. So this is the Fermi function as we shown earlier. Again, this is the energy level on the y-axis, and then on the x-axis is the probability. And you know the maximum probability is 1, and here is 0. And in the middle, this is what we define the EF. It's a reference level, because this tells you the half. So this is at some finite temperature, right? So this is not step function. This means temperature is higher than 0 Kelvin, and we have this kind of probability. So here, this is a probability, and this is available states, and then eventually we can get how many electrons occupy on those levels. So how do we do that? We have the available states and the probability, So for example, on the bottom, we have 10 states available, and the probability is 1. That means what? 1 means 100%. So that means you can occupy those 10 states, 100% probability. That means in total, you get 10 electrons. So if you do that, eventually you get the number of electrons on each level. And you can basically use the available states multiplied by the probability here. So on the bottom, you have 10, and the probability is 1. So you get 10. As you go up, so this is still like 10, because this is like 1. And here, almost is like 1. So still you got 10. Oops. In the middle here, for example here, your probability maybe is only 0.6. So then 10 times 0.6, you only get 6 electrons here. And then as you further move up, your probability will go down like 0.3. Then you get 3 electrons. And then 1, and so on. And on the top, because the probability goes to 0, then you get 0. So the key point is that the actual number of electrons depends on 2 factors. One is how many available states at each energy level, and then what is the probability for electrons to occupy. And then those 2 factors, if you multiply together, you will get the actual number of electrons. Any questions here? So I got one question. Can the number of electrons be changed on the different temperature? So here, I would say the probability will change as a function of temperature, as we showed in the previous slide, right? So with different temperature, then this probability will change. But the available states here will be determined by the semiconductor property, and then it won't change too much as function of temperature. So what will change as temperature is this probability, and then as a result, the number of electrons, of course, will change. If you have, let's say, higher temperature, then we get more spread out of the Fermi function, then the number of electrons will change. Any other questions? All right. So this is a simple example. And then let's look at a different example here. So in this case, this ladder system will have different, let's say, number of states on each energy level. So it's more like a triangular shape. So at the bottom, lower level, you have less number of states, available states. As you go up in the energy, then you get more available states. So if you have this kind of shape on the available states, then again, you need to consider the probability given by the Fermi function, which is always like this. Of course, depending on the temperature, then this transition, this slope will change. But this is like the EF. And here probability is 1, here probability is 0. So here the actual number of electrons on each level is again the product of these available states and the probability given by the Fermi function. So at the bottom, here we have 3, because the probability is 1, and then 7, and here 13. But here you are entering the transition region. Then the probability will be maybe 0.6. Then you get like 10. And then here, although the available states increase, but the probability decrease. So then the product is, for example, 5. and then here is 2, and then here is 0, because the probability is 0. If you consider those two factors, then the actual number of electrons, or we call the occupancy of the electron, will have this kind of shape. First increase and then decrease, because first increase because this available states increase with the energy level up, but the probability will go down as you increase the energy level. So eventually then this will go down. And this is the actual occupancy of the electron in this example. Any questions? What is meant by available states? You can think it's like empty seats in the classroom, right? If you think yourself is an electron, then the available states is available seats in the classroom that you can occupy, right? So this is how you think it. And then the other question, total electron on the graph is 40. Why 40? Oh, this is just an example. So this is just an example. So it does not mean anything real. This is just a simple example. We will discuss what is real in the silicon in the next slide. Okay, so this is what is real in the silicon. So again, we have this available states, and then if we correlate this with the energy band diagram as we showed before, so in the silicon or in general in the semiconductor, we have this valence band and conduction band, and in between we have this band gap, e.g. And as we discussed before, in the band gap, there's no available states. Electrons cannot occupy the levels in this band gap. So here on the right, we show the available states. So then for the electrons, then the available states start from this band edge EC, and as you further increase the energy, this is actually a parabolic function, like shape. So you will increase the number of states as you further increase of the energy. This is given by the silicon's property. We will not derive the equations for that, but this is the conclusion. So it's like the example in the earlier slide, like this one. So this is a simple example, but we assume here it's a triangular shape. As you further increase the energy level, then the number of available states increase. But in the real silicon, this is a parabolic function. It's not triangular function, but it's a parabolic function here. And then the higher the energy, more available states for the electrons. And we only care about the electrons in the conduction band. The reason is that in the valence band, what will contribute to the current is the hole. If you remember, we create the electron and hole pair. Once you, let's say, move one electron from the valence band to the conduction band, you will leave a vacancy, and this vacancy will become the hole. So similarly, in the holes, let's say in the valence band, the hole will have this so-called density of states of the holes, which starts from the EV. So then this is for hole to occupy, and here is for electrons to occupy. So for holes to occupy, the lower the energy level, the more available states for the holes to occupy. So they are kind of symmetric. So this is called the density of states of the electron. So what is the density of states? Because there are so many levels in the conduction band. So here, if you think of the ladder system here, that means so many levels means the distance between two levels is so close. So we can use a continuous function to represent that. But in this example, it's a discrete level. as we discussed earlier in the silicon. There's so many atoms, so the energy levels is so close. You can think it's a continuous function. So if you think it's a continuous function, then we can represent this function as Gc, and as a function of the energy level E. So then Gc is this one. This is a Gc for the density of states. So it's a parabolic function and it's continuous, as we discussed. So any questions here? Where are the states? So I couldn't quite get your question. So the states is in this energy band, and this is let's say this is energy level. You have different levels of energy, and the states means on a certain energy level, how many electrons you can put there in the system. So this Gc means at a particular energy level, then how many electrons you can put there at most, let's say. It's like a capacity of the classroom, if you remember the analogy we made earlier. So if you think you are an electron, and the density of states, you can think at that particular energy level, the capacity. You don't need to occupy all of them, but that is a maximum capacity. Any other questions? Okay, so if you think that is a capacity at a particular energy level, then this is the maximum available states the electrons can occupy. But as we said earlier, the electrons will not occupy all the space because it will be restricted by the Fermi function as we discussed earlier. So this is what we want to see. Again, this is the silicon's band diagram. You have the conduction band and valence band, and in between you have the energy band gap. So this is the GCE, that is the density of states of the electrons in the conduction band. You can think that is a function to give the maximum capacity at each energy level, and it's a parabolic function like this. But the actual electron density, or the electron occupancy, is given by, again, this density of states multiplied by the Fermi function. So this is the same as we showed in the earlier simple examples. You remember that ladder system, and then you have that available states, and then you have Fermi function. So the product of those two will give you the actual electron density in the silicon. So if you do that, you see here, this will start from the EC, the band edge, and then you will multiply here and here, you have something, and as you go up, then the density of states increase. So first it will increase, but eventually this Fermi function will go to 0. Then you will decrease the actual electron density. So this is the actual electron occupancy in the conduction band. So this is the electron density as a function of the energy. So electron will only occupy in this range. And then this starts from the band edge EC. And to make this simple, we will make one assumption. That is, we assume that the density of states is squeezed into the band edge EC, and then the electron density N, this is the electron density, is given by this formula. And NC is called the effective density of states in the conduction band. So this means if you squeeze this into a delta function, let's say. So here, if we assume all the electrons are squeezed into this band edge, then we get this NC to represent the capacity of the states in the band edge. And then if we have this NC, effective density of states, then we will use the Fermi function and the Fermi level, EF, to calculate what is the actual electron in the electron density in the conduction band. It's given by this formula. So this is very important formula. You are going to use this many times in the following homeworks and exams. So you need to pay attention to this one. So this N, if you remember, we have this small n. It's the electron density in the silicon. And it has a unit like the per centimeter cubed. So then that means 1 centimeter cube of the silicon volume and how many electrons there. And it's given by this NC multiplied by the exponential function EF minus EC over KT. So EF is this EF, and EC is the band edge here, EC. So basically the EF minus EC is the distance here between the Fermi level and the band edge. And this is a negative number because EF is lower than EC, so EF minus EC will be a negative number. So it's an exponential negative number divided by KT. KT is the thermal energy, as we discussed earlier. And for silicon, this NC is given by this parameter 2.8 times 10 to the power 19 per centimeter cubed. So this is a physical constant for silicon. So any questions here? So here the similar argument can be applied to the hole, because hole is in the valence band and it will have similar shape of the density of states, this GVE, and then the actual hole occupancy in the valence band will be a product of these densities of states and then the hole's probability. So be careful here for the hole. The hole's probability is opposite to the electron. So if the electron's Fermi function, if you recall, the Fermi function of the electron is something like this, then the Fermi function for the hole will be reversed like this. Why is that? Because electron and hole is a pair, right? If there's a hole, that means there's a vacancy of electron. So it's 1 over the Fermi function of the electron. That will be the probability to find the hole. So they are mirrored by the center of the EF. This is a little bit skewed, but this is half. So this is opposite, or let's say mirrored from the electron's Fermi function respect to the center here. So then hole will also have this similar kind of occupancy in the valence band. Then the hole's density, we use a small p to represent the hole's density, is also given by this similar equation. And this NV is called the effective density of states of the valence band. This is a different number in the silicon, and this number is 1.04 times 10 to the power 19 per centimeter cubed. And then this under the, let's say, exponential function, the EF is here and the EV is here. So the distance between the EF and EV will determine the hole's density. Again, this EF minus EV is a negative number because EV is lower than EF. So any questions? Okay, so let's have a summary. And here the most important take-home message are those two equations. So this is a way to calculate the electron density in the silicon or in general in semiconductor, and it's given by this formula. And Nc here is a physical constant, and for silicon is this number. So what only will change is the EF, and we'll discuss how the EF will change later. But if you think about the electron density in the silicon, you only care about where the EF is, because EC is the physical constant. And then, of course, you care about the temperature. So only the EF and the KT will change, because the NC and EC are physical constants. Similarly, for the hole density, then only you will care about the EF and the KT. And the NV and EV are physical constants. So for silicon, here are the exact number for the NC and NV. But for simplicity in this class, we will assume NC equals to NV equals to 10 to the power 19. We only care about the orders of magnitude. So later in your homework and in the exam, we will state that you use this NC equals to NV equals to 10 to the power 19 to simplify the calculation. Any questions? Got one question. Do the N and P relate to the N-type and P-type transistors? Yes, exactly. So this is what we are going to discuss later in the lecture, maybe lectures 7 or 8. Yeah, so that's why we will start with the N-type and P-type doping for the silicon, because later when we make the NMOS and PMOS transistor, and then this is related. Stay tuned for that. Okay, let me stop the recording for the first part.